Nice to see you, all my colleagues. I hope you're all okay. And now we continue our seminars. And let me introduce our speaker today. It's Yuriy Semenov. He's a professor from Institute of Hydromechanics, National Academy of Science of Ukraine. And title of his talk is Nonlinear Two-Dimensional Problems of Free Surface and Interface Flows. Welcome, Yuriy.
Thank you, Chairman, for introduction. Presentation today title Nonlinear Two-Dimensional Problems of Free Surface and Interface Flows. The title of presentation is quite general and includes many free boundary problems. It is because I would like to present not only one particular problem, rather than methodology developed for solving this class of two-dimensional problems. One sort of fluid mechanics problem arising in industrial applications are those dealing with free boundaries. Free boundaries problems are nonlinear because flow region is unknown and have to be determined as part of the solution. You can see cavitation in a marine propeller, cavitation in inducer centrifugal pump, supercavitation torpedo rocket. As you know, this topic of my department and the Institute of Hydrodynamics, where this technology was invented by famous Professor Lagvinovich. Vladimir Georgievich. Other problem is impact problem, slamming, hydrofoil cavitation for hydrofoil sub, so-called deck impact, deck slamming, when waves hit the platform bottom. Also at the Institute of Technical Mechanics, Ukraine Academy of Sciences was developed technology, vibro rotary well drilling. Now its technology is used for water wells, but I have no information application this technology for oil drilling. I start because I would like to speak more about methodology. I start with methods you well may know. It is a classical Helmholtz-Kirchhoff method for solving free streamline flow over the flat plate. As you know, complex variables are a powerful tool for solving free boundary problems. It is because the complex function satisfies the condition of incompressibility and zero vorticity. The problem is only to find a such complex function which satisfies kinematic boundary condition on the body and dynamic boundary condition on the free surface, or interface with additional condition. So here is shown method, Kirchhoff method, function zeta, physical plane is shown, then function zeta is an inverse function of complex velocity, and it is shown also plane zeta, and plane W, complex potential plane. So to solve problem, we need to conformally map this half plane with without semicircle to the cut in W plane. So unfortunately, equation not disappears. Awesome. So then Joukowsky-Mitchell method, they have made significant progress in solving free streamline flows, introducing the parameter plane or zeta plane. Because we don't
Excuse
know.
me, we cannot see anything. No, because your screen is very, very small. I cannot see anything.
But there is some corruption.
Sorry, you can share your screen in all screen because it's very, very small. No, 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 no. Your screen in reader. Share on all screen.
I can see all slides, even slide not fitted into the screen. So, can you see the title of the slide, Mitchell-Joukowsky method? Can you see my slide?
Yes, we mentioned the Joukowsky method. We see, but some formula is disappears. Now it's
Corrupt.
okay. Yes, yes, yes.
Fortunately, formula corrupted. It's a problem with phone. So Joukowsky and Mitchell introduced parameter zeta plane and proposed to determine function of complex potential and function of complex onto the parameter plane. It is much easier to conformally map half plane onto the region of the complex potential and region of the complex velocity or function omega as shown here in this figure. So then I need to, next step in methodology was made by Chaplygin. Before I will talk about Chaplygin method, I need to mention two basic properties of complex function which will be used in Chaplygin's method. First point is that how we can extend a function defined in the region R1 to the symmetric region R2, and about the straight line which satisfy following boundary conditions. For example, on this straight line, we wish to have imaginary part of the complex function equal to 0 or constant. Then we need to put in the symmetric point of the about this straight line the complex conjugate value of the function. If we wish to have constant magnitude of the complex function, we need to put in the symmetric point inverse singularity of inverse order. So using these main properties, Chaplygin very quickly found a solution of many free streamline problem, and it was surprising for his colleagues in that time. So, for example, we can see that complex velocity has 0 point at point C, where streamlines divided in two streamlines. And that's all. There is no any point where velocity equal to 0 or equal to infinity. It means that complex velocity has only one 0 at the parameter plane. But then we need to extend this point into the symmetric region of the parameter plane, and then we easily can find the expression for the complex velocity. Similarly, we can do with the derivative of the complex potential. This is Chaplygin using these properties of complex function and properties how to symmetrically extend the function into symmetric region. It's a very powerful tool to construct a function, complex function, which satisfy given boundary condition. It may be constant argument or constant magnitude. However, most of problems, modern problems, such as gravity flow, unsteady flow, we have a situation when velocity magnitude is changing on the boundary, and also for curvilinear bodies, argument of complex function is continuously changing. In this, for this case, it is I derived integral formula by using the symmetric principle and Chaplygin special point method. But it is not. Then, unfortunately, formula is invisible here. Maybe, sorry, maybe I need to go to.
But yes,
I,
yes. I propose
I
to
will.
presentation form. Yes.
One moment. Maybe this will be better.
Yeah, sure.
On the same. Let's say.
Unfortunately. Okay.
So I derived two integral formulas. One formula is solving a mixed boundary value problem. It means on the real part of the first quadrant is given argument of complex function. On the imaginary axis of the first quadrant is given magnitude of complex function, some arbitrary function. So, and finally, we can find equation, integral equation, which provide a complex function which satisfy given boundary conditions. This is another integral formula for solving uniform boundary value problem. It means on the both imaginary and real axis is given argument or magnitude of the complex function. So we can also obtain integral equation for this boundary conditions. So the integral, I call it this formula and this approach as integral Hodograph method. That is extension of the classical Hodograph method for solving various free boundary problems. Now this method was used to solve following classical problems. For example, gravity and cavitation hydrofoil need a free surface, and so on. So I will mention about these problems later. Now I would like to present how to apply this method for particular problem. This is actually the problem which I'm working currently. Last time, many researchers are interested about ice-water structure interaction. It because polar regions is melting due to global climate change and open new routes and new areas for resource exploration. So this topic related to ice is very popular at fluid mechanics community currently. So we, to solve this problem, we use following assumption: flow incompressible, elastic sheet is enough thing to apply Kassarat theory, hyperelastic shells. Hydrodynamic pressure on the interface is the same as pressure conditioning independent of the elastic sheet. The obstruction on the bottom may generate flexural gravity waves extending to infinity in both upstream and downstream direction. The flow and shape of the elastic sheet don't change in time relative to the obstruction. So we consider steady flow. Flexural gravity waves literature review. So there are many papers. This is only small part of that can be found in journals last decade. most of papers currently are dealing with linear theories. However, nonlinear effects is very significant for this problem, and it will be shown in the results of this presentation. So we need to formulate boundary value problem. So for the we introduce complex function phi and psi. Stream function phi is potential, and we easily can formulate boundary condition, which is the stream function is constant on the bottom equal to 0, and pre-stream function equal to unit on the interface, and also at the interface there is dynamic boundary conditions, which determines the relation between velocity and pressure on the interface. So Godograph method, we now apply classical Godograph method to derive complex derivative of the complex potential, because parameter plane is first quadrant, complex potential plane is strip, so it's elementary to find conformal mapping one region to another, and it means that complex potential as function of the parameter plane easily can be found. On the to determine the complex velocity function, it's more complicated problem, because velocity on the interface changes, is variable. So as well as argument of the velocity is variable on the bottom. So applying integral formula, which can be shown previously, we can easily find expression for the complex velocity. Joukowski-Chaplygin introduced zeta parameter plane, zeta plane, and proposed to find two functions. One is complex velocity, or logarithm of complex velocity, you can see in figure omega. And another is W plane, it's just cut of the half infinite cut. Then using Christoffel-Schwarz integral, we can find this function, required function. Next slide, please. Then, before I will start to talk about Chaplygin singular point method, I will introduce about symmetry principle and Liouville theorem. Here shown two regions, region L1 and the region symmetric region R2, and boundary sigma. We wish to extend function from region 1 to 2. And there are two kinds of boundary conditions. First is the real imaginary part equal to 0. Then we need to put in the symmetric point the singularity or 0 of complex conjugate value. Or if we wish to provide on this line sigma constant magnitude of complex function, we need to put a singularity of inverse order. Finally, if we have many, n number of zeros and then m number of polars of complex function, then and we know all the polars and zeros of function, then according to Liouville theorem, we can find the complex function as shown in this formula. Next slide, please. Here, Chaplygin singular point method. So we need to analyze a singular point, special point actually. Special point is 0 point, stagnation point C, and here at point C is mapped in the parameter plane to is unit. So we can put in the function complex velocity 0 nominator is 1 minus zeta, because 0 of the first order. Then we need extend extend the first quadrant, which is parameter plane region, to the all complex plane, to the point C prime, it's minus. And then to provide magnitude along the imaginary axis, magnitude constant along the imaginary axis, we need to put the same special point inverse order. That means we need to put it point -1 pole. And that's all. There is no other point where the function can be 0 or infinity. This is, we easily build complex velocity. Similarly, we can build a derivative of the complex potential, because we have 0 at point C, 0 of the second order, because the argument changed to 2 pi at point C, while at point the parameter plane zeta, it is changed only pi. Then at point D, we have pole of the second order on this, because same angle. Also, then we need to extend the function to the left half plane and lower plane. When we gather in all these symmetric points, singularity at symmetric points, we can easily write expression for the derivative of the complex potential. Please, next slide. But in practical, we need to solve problem with change, with varying magnitude velocities, with varying argument of the complex function. So we formulate boundary conditions. So at this stage, we assume that we know the function of the argument along the real axis, we know function of magnitude along the imaginary axis. Then we discretize this axis and assume that the function is constant at each interval. Because function constant, we can apply symmetry principle. And we can write a lot of, at each point we can put 0 or polar with some value of order. Then we can gather in all these single special point, and you can see we can write this equation for the function. And then one step is when we transform infinite product to the integral and introduce change of the instead of step change of the in argument, we introduce continuous function. So finally, we can obtain equation star, red star, that is integral equation which determines a complex function with given boundary conditions, with given argument on the real axis and with given magnitude on the imaginary axis. Next slide, please. Doing similarly, we can derive the integral formula for solving uniform boundary value problem. This function where theta is given, and function on the both real and imaginary axis of the first parameter. Then this function determines the required complex function. Substituting values on the real axis or substituting value on the imaginary axis, we can verify that this is boundary conditions are satisfied. Next, please. Here I already told that application of this method for solving free boundary problems. Next slide, please. This is particular problem which I would like to consider in this presentation. This is a flow in channel covered ice sheet, a channel with obstruction on the bottom. I already talked about this. Next slide, please. This is literature on this problem. Currently, most of paper published in best journals are based on linear theories. So nonlinear theory is still not easy and not many papers. And what we can find in literature dealing with nonlinear response of floating ice to a moving load. So on some special problems, and just interaction of the wave and ice sheet without interaction of the structure, just wave ice interaction. So next slide, please. So here shown boundary conditions, formulation of the problem. We introduce complex potential, and so phi and psi stream function should satisfy Laplace equation, and boundary kinematic boundary condition just constant stream function on the bottom 0 on the interface unit, and dynamic boundary condition which determines which accounts bending of the ice sheet. So apply, next slide please. Apply the Dobrov method. Following Joukowsky, we can easy to find the derivative of complex potential, because in this special case, the complex plane is just strip, parameter plane is just first quadrant, so its elementary transformation is W is logarithm of zeta. If we know to determine the mapping function z on zeta, we need also to determine the complex velocity dv dz. Next slide, please. At this stage, we assume
Sorry, I have one question about your strategy. Not clear why you use plane method for special problem. Well, because if you really look at on your picture, you have a 3D problem, yeah? And in fact, you want to consider section 3D biplane, correct? Is not, for me, not clear. Is not flow on the plane. In fact, you consider section, intersection between 3D and by some plane. Not clear why use method connect with plane flow. Explain me, please, your logic.
I need to explain the formulation of the problem, physical formulation.
Yeah.
We consider.
I think about physics. Look at you have 3D problem. Okay, no,
not 3D. No, why 3D?
Yeah, it's real physical problem is 3D, because if you consider some ocean or some mass of water who flow along some bottom, yeah, it's 3D problem, because you have length, width, and height. You take intersection.
No, I agree with you that real water is 3D. It's correct. You're correct.
Yeah.
But when we are solving problem, we can make some assumption, and we are solving problem within this assumption. I explained at the beginning of the title presentation that I am considering two-dimensional problems. It means that body on the bottom is a cylindrical body extending perpendicular to the inflow velocity. If this body is enough long in the plane perpendicular to the plane of flow, then we consider this flow as two-dimensional. And my interest in this presentation is to determine properties of two-dimensional flow. Okay?
Oh, I understand, but my opinion is not correct from physical point of view. It's not correct. No, because look, you have flow. Okay,
What
no
means
problem.
correct? What means incorrect? Each researcher has the right to make assumption which he wants. Are you agree with that?
Yeah, okay. Okay, thank you.
Okay, it's good. Continued. And so what we have, complex value. Okay, so we need second, we need to determine expression for the complex velocity. At this stage, we assume that we know the function of the argument on the bottom, and we know function magnitude of the velocity on the interface. So then apply an integral formula as shown before. We easily obtain complex velocity and mapping function, which maps first quadrant onto the zeta plane. What is the next slide, please? Next slide, please. Are you hear me? Are you hear me? Okay, okay. Are you hear me?
Yeah, yes. We have.
Okay.
You.
Thank you. So here shown what is difficulties even in two-dimensional problems. We have a lot of difficulties. So it because that is why I did not see in literature three-dimensional or even two-dimensional did not see. So if you publish paper on 3D, it will be great. What is difficulties in this problem? It's logarithmic singularity. When we consider channel flow, we can calculate actually far upstream and far downstream about 5 thickness of the channel, 5 height of the channel. It's because you can see that parameter variable zeta and eta is exponentially depend on the potential, while potential just linearly depend on the distance x or s. So, okay, I will omit this detail. Go ahead. So, anyway, we can easily find the function complex complex velocity, changing variable from zeta to phi and psi, or complex potential. And this expression, next slide, please. Next slide. So here shown, yeah, please, this, yeah. So the expression of the mapping function is still contains two unknown function, which is beta on phi and velocity on eta, also on phi. But fortunately, we can easily derive the integral differential equation using changes of variable as shown in equation 20. Then using derivative of the mapping function, equation 21, we can easily obtain integral differential equation 22. Here you can see a function d beta d phi appears in both sides of this equation, and it is easily can be solved, of course, numerically using iterative procedure. To determine the function magnitude on the interface, more difficult problem, and this problem was solved numerically, a discretizing problem, choosing some nodes on the phi, on the potential axis phi, and then reducing the dynamic boundary conditions to the system of nonlinear equations, which is solved using Newton's method. Here shown the way. This also the difficulties on this step is that ice sheet is described equation which include higher order of the derivative of the interface. Fourth order derivative, you can see this is I counted here CP. You can see pressure coefficient on ice is second derivative of the curvature. This is difficult. However, it's possible to solve this system numerically. Next slide, please. Next slide, please. Okay. I already described it. This is what I told about numerical solution of the dynamic boundary condition. So you can see that the equation for the pressure contains second derivative of the curvature, and it represents some significant numerical difficulties and require higher order approximation of the interface. Next slide, please. Here, dispersion relation, applying linear small amplitude waves, we can substitute into dynamic boundary condition shape, or sinusoidal shape, and obtain the equation 33, which is the dispersion relation equation. In this slide is shown how we can derive dispersion relation in presence of ice using a dispersion relation without ice. So we just without ice, this is equation 34, it is without ice, and we just substitute another right hand side for the velocity and obtain equation 36, which is the dispersion relation. What we can see in this picture, that solid line correspond to the case without ice sheet, that free surface, and we can see that one fruit number corresponds to one wave number. For in this subcritical region, fruit less than 1, because fruit is based on the channel height. And but if there is ice sheet, we have another situation. There is some range of fruit number where we have no solution. Then we have fruit less than 1. We have two roots of this equation, and for supercritical regime, fruit number larger than 1, we have one root of this equation. So next slide, please. Here shown a verification of the numerical model. First, we compare our results with those published in literature for the free surface. Here shown results comparison with results Forbers and Schwartz for the flow over semicircular obstruction in channel with free surface. Also, I should say that in case of, in any case, free surface and ice sheet, we have introduced a damping condition because wave extends to infinity. But in calculation model, we have some finite length of the calculation region. So we introduce this artificial coefficient to get flat free surface far downstream. Next slide, please. Here shown results for subcritical flows. Here shown critical flows 0.66, and first figure 4a, here shown flood number 0.4 and different thicknesses of the ice sheet. We can see that different of the obstruction. The ice thickness is shown B over H 0.05 and different height of the obstruction. We can see that larger height of obstruction, larger straw of the free surface. But what is interesting in case of nonlinear, what is in case what we can find new knowledge that we have some limit of obstruction for which a solution can be obtained. For example, in figure B, the solid line correspond height of the obstruction 0.2, and we cannot obtain solution, convergent solution for larger obstruction. On the figure 5 is shown one set corresponding to one set subcritical solution. For example, for fruit number 0.33, we can use height, or for fruit 0.4, we can use height of obstruction 0.033. But for fruit number 0.6, we can obtain solution only for height of the obstruction 0.1. So as we approach to the critical fruit number, the height of the obstruction getting smaller and smaller, for which steady solution can be obtained. Next, we consider supercritical channel ice supercritical and channel subcritical flows. That means that fruit less than 1, but larger than critical value 0.66. Next slide, please. Here shown bending moment and pressure coefficient, bending moment, and free interface shape for this regime. So height obstruction is 0.5. This is A, picture A, and B, figure for obstruction 0.1. What we can see is that if fruit number enough large, far from the critical fruit number, we cannot see some effect of the ice sheet on the interface. However, we can see effect of the ice sheet in the bending moment and pressure coefficient, because for this case we have two roots of the dispersion relation, one with small wave number, so caused by elastic sheet, and another is gravity wave, as usually it's much larger. So here shown the same results shown in figure B, but for larger height of the obstruction. What interesting that both elastic sheet wave can be seen for upstream and downstream. In linear series situation, they predict different. They predict that elastic sheet wave can exist upstream and go downstream only gravity wave. But in this nonlinear solution, we can see that there is some region of where these two waves interact each other. Here shown, next slide please. Here shown similar results, but for smaller fruit number, 0.8. A little bit closer to the critical fruit number. And we can see because elastic wave length approaches to the gravity wavelength, so they interact more significantly. And again, for small height of the obstruction, the interface almost sinusoidal downstream, but we can see appearance of the elastic wave upstream. On the figure B is shown the same results, but for larger obstruction on the bottom. So we can see that downstream there is interaction of two waves, elastic and gravity waves. And next slide, please.
Yuri, excuse me. How you take into account gravity? Because in your model, I cannot see any gravity term.
Gravity term is included into dynamic boundary condition. Because fruit number, we have fruit number, fruit number is in gravity.
It's very strange because gravity acts on all your flow, not on the boundary.
Yes, of course, but gravity does not change the Laplace equation. It's still Laplace equation. Gravity appears only in boundary condition.
But in this case, in your model must be appear new term which connect with gravity. Is the logic.
Okay, please show previous slides. List slides up. Next. Next, formulation of the problem.
Yeah.
Because the question is really regarding to formulation of the problem. Next.
Oh, no.
Next.
Yeah.
Next.
No,
Up. Please, up. Father, formulation of, no. Up.
What is page? What is page number?
Page number, yeah, just one moment. Which page number is 13.
13.
Slide number 13.
13.
No.
13.
1-3.
Yet free up slide, please. What? Wait,
Here. Stop.
Okay. Yeah.
Stop. Equation 4. But equation 4 is fruit number introduced, and then Bernoulli equation. Here appears gravity, but equation 4 is written in undimensioned form, and gravity G is included into the fruit number. Okay?
Roma.
Yeah. So I understand your logic, but it's not correct from physical point of view.
But your question about
No. Look at Laplace equation in all flow. It's very strange because if you want to take into account gravity acts on all flow, not only interface. For this reason, I don't understand your logic. It's not enough. Your boundary condition is not enough for taking into account gravity. Do you understand me?
You understand that you don't understand me.
Okay, no question. Yeah, I clear your logic, but I have another.
But excuse me,
Yeah.
but it is correct boundary condition 4. Equation 4 is correct? It is Bernoulli equation. It's just Bernoulli equation. Bernoulli equation is correct physically.
Under some
Maybe.
assumption. Under some assumption, correct.
Yes, but I explained assumption before.
Maybe not 4, maybe 6 boundary condition. F contains the gravity. F a fruit.
This curvature, yeah?
Yes, F fruit
six boundary-
number and 6 equation contains F, which contains the gravity.
No, equation 6 is due to elastic sheet. In case if elastic sheet is absent, then pressure ice equal to 0. So
No, it's
P ice equal PA. In case without elastic sheet, pressure ice equal to pressure atmosphere. So at this term disappears, appears only velocity number of feet squared. This is velocity, and the gravity term G y. This is only 2 terms with a free surface. With interface 3 terms. So I very surprised that you're not happy with the Bernoulli equation in terms to account gravity. Bernoulli equation accounts gravity.
Yeah,
And
of
I
course.
didn't see any problem.
No, my question connect with another story. Look, in fact, you consider, no, in real life, you consider 3D problem. Or
No.
no, 3D problem. Because all your pictures, this is intersection 3D problem by plane. By plane. No.
Roma, it's a similar Heli show self. Yes, in general it's 3D, but we consider so very small with weight, yes, and you obtain 2D dimension.
Yeah, but this is
it's like here, similar like here, if I understand right.
But
You
okay.
obtain 2-dimensional problem.
Yeah,
but it's enough to consider only taking into account gravity only in the interfaces. In this case,
in the title of presentation is shown 2-dimensional problem. What we are talking? We are talking about mathematics, not physics. Now my presentation about mathematics. Physics we can discuss.
Okay, please again. So maybe continue.
Yeah, thank you.
But anyway, I thank you for your question. I'm happy that it is, makes into some exercises. So now 35, slide 25. Here's on channel supercritical flows. Actually, in case of free surface, next slide, please. In case of, next slide, please, 26. Oh, in case of free surface flows, for supercritical regime, we have two solutions. One is just perturbed flow interface, and second is soliton wave. So we have no wave in surface downstream. Now please return to 25. But in case of the elastic sheet, we can see that interface downstream makes wave which oscillate around the perturbed solution. And actually we was not able to obtain similar results for soliton wave. It's not clear exist or not exist. Okay, the next slide, please. Next slide, please. So this is conclusion. A fully nonlinear solution of steady flexural gravity waves in a channel with an obstruction is presented. The solution is obtained in the form of system of integral equations which are solved numerically. The interface shape between ice sheet and the liquid exhibits superposition of elastic and gravity waves. However, the visibility of superposition significantly depends on the ratio fruit to fruit critical and the height of the abstraction. The elastic wave decay downstream. The decay becomes more slowly as fruit number approaches critical fruit number. So I can. This is what I would like to present in the first part of my presentation. If you wish to continue the presentation, we can continue because there is slides. I would like to just a review of problems where the integral photograph method was applied. So please, next slide. Here shown problem of cavitating hydrofoil beneath free surface. So on the right hand pictures you can see different cavities past the flat plate, cavitating flat plate. On the figure left hand side you can see how free surface depends on the fruit number. Here, x coordinate is normalized to fruit number to show all results in one figure. The paper was published in Journal of Fluid Mechanics. Next slide, please. Here shown results for the water entry of oblique water entry of the wedge. The question was how the inflow angle of the flow or angle of the entry can be what range of the angle of the entry such that flow not separated from the wedge side. And the shown experiment on the right hand side of this slide is shown experiments, and we determined that 1/3 of the flow separation corresponds to special behavior of the pressure on the leeward side of the wedge. So pressure only became negative, and for this case, even small amount of air makes the total separation of the flow from the wedge side. Next slide, please. Here shown results for the water entry of the flat plate. It's like for landing, aircraft landing or some similar situation. The problem also, real world also three-dimensional, but two-dimensional problems very very useful to understanding the physics of this phenomenon. Next slide, please. Liquid wedge impact on the solid wall. The wave crest can be modeled as the liquid wedge, and here shown results for the impact of liquid wedge with a flat plate and with some body in the form of a corner. So this also was published in Royal Society. Next slide, please. Here, a problem of collision of two liquid wedge. We can see if two liquid wedge are symmetrically, then we obtain symmetrical results as shown in the figure. Figure one. As one wedge has a little bit larger angle, then we can see that splash jet deviate from the axis, x-axis, and as the angle increases, this collision of the tip point of the splash jet with the inflow wedge. What is interesting then, and this is solution completely not correspond to the physical reality, because here shown in figure how the splash jet penetrate into the liquid. That impossible, completely impossible from physics point of view. But what is interesting that we can see some small area without liquid. So it's on the lower figure in the center. And this is very important in terms of how aeration of the water. When two masses of water collided, they always produce some capturing of air. And here shown the picture which demonstrates the situation which maybe you also observe it in the beach of sea. That we have some very mix of air and liquid after the overtuning of the crest of the wave. Next slide, please. Here shown another problem. It's also liquids, but different densities. What happens if a liquid same angle but different? It's just one figure, and more figure can be found in the paper. And next slide, please. Here shown Heli-Show. All problems presented before are either steady flows or self-similar flows. So they self-similar, it means that we can exclude time from consideration, and that significantly simplify solution of the problem. However, also was solved one problem, time dependent. It is Heli-Show flows, and here dash line outline is this statement of the problem. So we need to find potential which satisfy Laplace equation and velocity which obeys Darcy law. So we introduce complex potential and apply the integral photograph method to derive the complex velocity and derivative of the complex potential. Also, considering kinematic boundary conditions, we can derive Polo-Barry-Navagalin equation in more general form. Next slide, please. Here results for Heli-Show flow. In the first figure is shown velocity distribution for the gas bubble corresponding to this form of gas bubble. And here on the next picture is shown the calculation in the corner geometry, time evolution of the interface, free surface, and experimental results from the paper of Lagency and Kauder. And another geometry is shown in the lower figure. How to free surface when we suction air is sucked in the origin of this evolution, starting from kind of arc of circle, and how the arc of circle changes during time. Next slide, please. The integral photograph method has been developed for solving various nonlinear two-dimensional free boundary problems. Two proposed integral formulae make it easier to solve both the mixed and homogeneous boundary value problem for an analytical function defined in the first quadrant. The method has been applied for solving gravity flows, self-similar flows, cavity flows. It can reduce a free surface problem to the system of integral equations. Next step is to various time domain problem. Thank you again.
Thank you very much, Yuriy, for such interesting talks for us. Maybe so most of my colleagues, it's very interesting and some news, especially it's related with colleagues working with complex variables and complex mapping. So our colleagues, please, questions, comments? Questions. So, okay, I have some questions. So, Yura, I'm interested in is the first your problem when consider in the channel ice and waters. Do you have considered the initial position of your free boundary is smooth? Yes, is that correctly? Or
this is a steady flow. This is steady flow. And in terms of calculation, we assume it initially free surface shape, and then apply equation for ice.
Yeah, I understand it. But I'm interested in with you started with the smooth surface, yes, and then
not smooth,
not smooth, a non-smooth. But what singularity?
Actually, it does not any shape of the abstraction is okay. You can see actually results are shown for the semicircular abstraction. All results were shown. It's for semicircular abstraction as shown on the slide with verification of the numerical approach.
Okay, but if I understand right, in any case, if you started then in the smooth position with your boundary, you obtain the wedge, yes, and the smooth wedge, or you possible appears the corner, yes or no? It's possible in the consider situation all the time. Because, for example, global in time, you obtain the singularity then or no? Or the
yeah, you mean last slide? Your question is about last slide, yeah?
No, not only, but also yes, it's last slide also.
Of course, there is for Hileshow problem in case of suction of air and reducing area of bubble. We have some finite time beyond which we cannot calculate. When the free surface touches the origin of the body.
Yuriy, Natasha asked you about smoothness of your initial interface.
Yeah, of course. Initial interface, but then obtain non-smooth interface is, and then you obtain in suction problem. Yes, when obtain the singular free boundary. Yes, Yura.
According to semicircle, maybe yes.
Yes, sure, of course, but not.
But this is problem with solvability, such type free boundary problem.
There is no, Natasha, there is no limitation to the geometry of the body.
It's very strange.
No, it's solvability is a suction problem. It's local solvability, but global maybe it's non-uniqueness. Maybe it's possible rising
and non-existence.
No, I did not meet any difficulties with geometry of the board. Of course, I consider
Yuriy,
it.
If you have cusp, it's not problem for you. If you have cusp on interface.
But if you see statement of the problem, you can find that results are shown for the problem with surface tension, including surface tension. In this case, there is no cusp on the interface.
Roman, so it's not considered if the initial position you have the cusp and what's happened then. No. If I understand right, Yuriy considers the case in the smooth position and that's what's happened after that. Yes?
Yeah.
Without, yes, without
Yeah,
surface.
of course. It's for with suction, Helishov with suction, for example. Okay, yet questions, comments? Okay, now then.
Можно я по-русски?
Можно.
Юрий,
Please.
подскажи мне, подход Майлса Луковского используется в этих задачах 3D вместо комплексного потенциала?
Я так сказать, не имел счастья заниматься вот этими методиками, которые вы назвали. Поэтому я не могу так ответить на вопрос однозначно.
Но она считается эффективной, это подход для нелинейных колебаний жидкости.
Для колебания жидкости. Ну вы же где-нибудь слышали колебания жидкости в моей презентации?
Ну, по крайней мере, оператор Лапласа был.
Нет, но это же не значит, что он колеблется. Что
Не,
колебания
ну,
есть. Нет, я
нет,
не рассматривал
просто интересно.
колебательных задач. Я вообще повторял несколько раз. Я
То есть там
рассматривал
лечение
стационарные задачи
Закону
и
Бернули.
задачи автомодельные.
Ну, уравнение Бернули, аэродинамика, что говорю.
На границе закон Бернули, а в области у вас типа закона Дарси.
Да, но
Ну,
метод
так-
Гадографа, конечно, очень наглядный. И картинка, конечно, понятна. То есть метод Гадографа, который, в принципе, конечно, очень наглядный. Но это, видимо, потому что 2D, да?
Да, в 2D
Ну,
он хорошо работает, насколько я понимаю.
Ну,
Это
Ну и метод комплексного потенциала тоже.
Владимир Федорович, это условное 2D. На самом деле, я не знаю, почему они так называют. Это не совсем корректно.
Ну, X и Y у тебя переменные.
Не, я понимаю, что
Ну,
формально,
поэтому в этой
да.
задаче модельной
На
плоской.
самом деле это 1D problem. 1D, классическая 1D problem.
Нет, Ром, это как бы...
Плюс свободно.
Нет, Рома, ну вот смотри,
2D
у тебя,
это у тебя вот
ячейка Helishov, у тебя 3D или 2D?
Смотри, как ты, если ты будешь...
Ячейка Helishov, у тебя рассматривается 2D, у тебя 2D, который
это
он...
вы рассматриваете. Есть народ и в 3D рассматривает.
Есть рассматривать, не, ну можно и многомерную рассматривать, да.
Наташа,
Ну,
дай закончить. Значит,
Да.
классическая 2D, это у тебя вот плоскость, и есть на ней лежит жидкость. И ты
Да.
рассматриваешь ширину,
Правильно.
а
И
это
жидкость между двумя плоскостями зажата. Вот представь себе канал вот
здесь
такой.
другая задача, здесь другая задача совершенно. У тебя есть подложка, а на ней есть жидкость. И на этой поверхности...
это уже трехмерная задача. Вы скатываетесь на трехмерную.
Ну, вы же на рисунке нарисовали вот подложка, жидкость и свободная поверхность. Или я что-то...
Нет, не так.
Так?
Двумерная – это когда в третьей координате вы можете в третью ввести физически, но в ней идентичные движения происходят.
Ага.
То есть как
я
координата z не меняется, а течение в плоскости xy остается таким
Ага.
же.
То есть
Вот
вы
это и есть
вообще реально, просто
задача.
роль тогда подложки у вас это просто твердая стенка, грубо говоря, на поверхности.
Ну да.
Потому что традиционно, как бы, ну, понимаете, что я вас, собственно, пытал. Потому что мы рассматриваем подобные задачи, только в другом чуть контексте, они из навье-стокса получаются. Как только вы начинаете гравитацию хотеть учесть, у вас сразу в навье-стокс появляется гравитационный теорем и так далее, и так далее. То есть, на самом деле, вы делаете нечто другое, как я понимаю. То есть, вы просто берете даже самую плоскость, и у вас, грубо говоря, есть стенка, и вот от этой стенки жидкость начинает двигаться вдоль плоскости. Вот так надо понимать тогда.
Не, ну, двухмерное это есть двухмерное, когда в третьей координате течения идентичны, не зависят. Они все такие же, как при любом другом координате.
То есть,
Это-
по сути, у тебя ничего не меняется, Рома. У тебя
Ну, плюс,
меняется
как бы, понимаешь, то есть,
фиксирование.
значит, дальше, как только вы хотите, чтобы у вас уравнение с границы было, ну, гравитация училась, полагаете, что у вас это ваша жидкость тонкая достаточно. Иначе это не так. А раз вы предполагаете, что она тонкая, значит, где-то должно быть предположение, ну, а-ля shallow water. Тоже я его не увидел, например. То есть у меня очень много вопросов по ходу возникло. Ну, как бы, что задал бы человека.
Ну, кстати, там я все ссылки на публикации привел,
Я
поэтому
видел, что на GFM все там.
вы можете ознакомиться более, как говорится,
Да,
детально.
я гляну.
Well, I think it's all my questions.
Роман.
Now in the discussion, maybe we
Роман, я
our
помнишь,
maybe our official part of seminars, and then we talk without with seminars, but during with our meeting. Okay? So, Сереж, все, нашу английскую часть можно заканчивать, не записывать дальше, а все остальное можно еще пообщаться, если есть вопросы.
Владимир Федорович.